One thing that crystal field theory can't deal with is ligand-metal pi bonding. So what do you mean that ligands can pi bond? So in the same way that we thought about sigma bonding between the metal and the ligand as being the ligand with an orbital that's pointed directly toward the metal, pi bonding between a metal and a ligand would be the ligand orbital being oriented side-on to the metal orbital. So you can see in the picture on the screen, as well as here I'll draw for you, that you could imagine one of these d orbitals, and it would have appropriate symmetry to interact with a p orbital that's oriented sideways instead of just a p orbital that's oriented head-on. Okay, so how can we think about how to generate molecular orbitals, the symmetries of the molecular orbitals that are produced by pi bonding? So here we're going to imagine, this is challenging, so we're going to imagine on each ligand, we're going to picture a p orbital that's oriented sort of sideways, like in the plane, and then we're also going to think about the one that's sort of pointed above and below the metal. Okay, so there's two here, I'll draw them in different colors. There's two p orbitals that we're thinking about here at the same time. Okay, and we're going to think about how those, so now there's 6 orbitals overall, and we're going to think about how they change as we do each of these operations. All right, this is going to be fun. So, if we imagine those 12 orbitals, if we do the identity operation, this one's easy, we're going to have 12 orbitals stay the same. If we do the C3, all of the atoms move, so 0 of them stay the same. If we do the C2, that's through the bonds, so through the bonds this way, all of the atoms move, so that's 0. Now, if we do the C4, okay, so 2 of the atoms stay the same. But if you think about doing a C4 through the top of those orbitals, then you see that one of them turns 90 degrees and the other one turns 90 degrees. So they're not in the same places that they were before. So we get 0. Okay. If we do the C2, that is the C4 twice. So this is the C2 that's through the bonds. Okay. If we do that, or we could, imagine drawing the one through the thing we have. We do the C2 through here. Now, what we'll end up with is that this purple orbital will be pointed the opposite way, and the green orbital will be pointed the opposite way, because we're sort of looking down on them, and as they're oriented pi relative to the metal. The metal's underneath this picture here. So when we do that, we'll see that both of our orbitals on this top ligand and the bottom ligand, both of those are now pointed in the opposite direction. So that's going to give us a -4. There are 4 orbitals that are all pointed the opposite way. Okay. Inversion, everything moves, 0. S4, everything moves, 0. S6, everything moves, 0. Sigma H. So when we cut through all of the orbitals, okay, then they're all going to be pointed sort of 90 degrees from where they were, so we get nothing there. And then sigma D, we're cutting through 2 of the atoms, but again, the orbitals aren't really symmetric, just trust me, we're going to get a 0. So this one is really challenging. It might take you a little while to visualize each of these orbitals. The key, it is not so much important to me that you be able to reproduce this derivation as that you be able to follow along and see where we're going with the pi bonding. So give yourself some grace, this is going to be okay. So we have a reducible representation for pi bonding p orbitals on the ligands, a group of pi bonding p orbitals. If we reduce this representation, that's a part you would know how to do, then we're going to get a T1G, a T2G, a T1U, and a T2U. Okay, now if we take those over to our molecular orbital, or our diagram over on that we sort of had before. So this is the group of sigma bonding orbitals. And then we could imagine adding our pi orbitals. The most important piece here is that before in our diagram, the T2G metal orbitals were non-bonding. They didn't have anybody to bond with. And now we see that they do have someone to bond with. They're going to have some ligand group orbitals. The question is, are the orbitals, so we could imagine that there could be both filled group orbitals that are down here below the sigma bonding orbitals. 5, 6, 7, 8, 9, 10, 11, 12. Okay, and so then we can imagine that one of those is the T2G. And so then we said that we had kind of the EG orbitals here, your EG star. And then the other EGs are down here. We're just going to draw part of this. Okay, and so if we had lower energy T2G orbitals, then that would make the energy of the T2G orbitals go up. So we can draw that. So the T2G orbitals would go up and they would be here. So these would be, they're sort of formally anti-bonding, but that's really okay. And then we'd have the bonding orbitals down here. The alternative possibility is what if instead, depending on the ligand, if instead the ligand pi orbitals were actually unfilled, and so they were up here. We're just imagining all of these ligand orbitals up here. They're all the same energy, and some of them are T2G. And so in that case, that would make the T2G orbitals go down because these would be the bonding T2G orbitals. They would go down relative to the metal, and then the anti-bonding ones would be up here somewhere. Okay, so relative to the sigma bonding case, which I'm going to show here in black, so this is T2G non-bonding, we could either have, depending on the energies of the ligand orbitals, we could either imagine the T2G orbitals the pi bonding brings down the T2G orbitals, or the pi bonding brings up the T2G orbitals. The pi bonding could bring down the T2G orbitals, or it could move up the metal T2G orbitals. And so we're going to define these two different possibilities as that if the T2G orbitals are low in energy, these are going to be examples of pi donor ligands. And if the T2G orbitals are high in energy and they're empty, these are going to be pi acceptor ligands. Because we can think about either we've got filled electrons and the metal is donating to fill these lower energy T2G, or the metal is donating empty electrons and that's going to increase delta. Okay, so so hold on to this concept of pi donor and pi acceptor ligands, and let's think about what this means for the spectrochemical series.